So today I'll be talking about convolutional neural networks for text. So convolutional neural networks were covered in the reading, and I'm going to talk about these in the context of prediction problems, specifically sentence classification for this particular thing. But I have a bunch of examples of how convolutional networks can be used for other things as well. But so this is our typical one where we have I hate this movie, I love this movie, and we need to predict very bad or very good or whatever. And our first try was Bag of Words, where we looked up scores for each of these and calculated the final scores. So this is the thing that I've been talking about the entire time. And I noted at the very beginning of the class that this is very easy to break because we can come up with things like, I don't love this movie, which becomes bad, and there's nothing I don't love about this movie, which becomes very good. So things like word order, etc., become very important. So we talked about continuous bag of words and the deep continuous bag of words. So the deep continuous bag of words, this was expressing feature combinations where you basically added up information about all the words in the sentence, and then you combine them in a nonlinear way. That could come up with things like feature 1 and feature 5 are active. So in other words, we have not and hate in the same sentence. So this is all reviewed. This is all stuff that I talked about before, if you remember. But what this cannot handle is not hate. So we know that not and hate exist in the sentence somewhere, but we don't know about their relative position, etc. Handling combinations, there's a bag of n-grams. So this, I don't think this was done in algorithms for NLP in particular, but I think if you've taken some NLP class somewhere or built a classifier at some point, this is something that you might have tried, which is basically where for each of your sequences of words in the sequence, if you have I hate this movie, you do each one individually, then you do I hate this movie, I hate this, and hate this movie, etc. And then you look up features for all of these, like unigrams, bigrams, and trigrams. And then you take the sum, you add the bias, you take the sum of all of these scores, and you get your scores for your classification. So this is nothing neural about this. This is just a regular feature-based model that that people have been creating for ages. And then you do this to get the probabilities. So people are familiar with this. You've used stuff like this before, maybe. So why would we want to use bag of n-grams? So the big motivation is it's able to capture combination features in a simple way, like don't love or not the best, or something like this. So don't love is a bigram that's very indicative of something being negative, and not the best is a trigram that's very indicative of something also being maybe negative or neutral at least. Another reason why is it works pretty well. So this is a Twitter thread that happened a little while ago. So on 2nd November 2016, there was a thing that said, we are releasing an open data set for theorem proving hot step. Can you beat our 83 accuracy baseline? And then about 2 hours later, Hal Domé posted on Twitter, sure, I'll try. I beat your 83 accuracy baseline with 85% by writing 10 lines worth of bag of n-gram feature extractors. So this is a pretty strong baseline for text classification, and it's a thing that appears in papers. It is a baseline, but it's pretty hard to beat because text classification is a relatively easy task that you can do pretty well by picking out just sequences of words. But what are the problems with bag of n-grams? So we had the same problem as before, like what I talked about with n-gram language modeling, which is parameter explosion, and also no sharing between similar words or n-grams. So this is kind of background, I guess, and then to very briefly cover some of the stuff in the reading. Are there any questions up until this point? I think maybe the stuff here is from elementary NLP. Yeah.
What was the text classification task?
Oh, this one? In the Twitter example? Oh, this was. That's a good question. I actually don't remember because I read the paper a while ago, but you can search for the hot step theorem proving task or whatever, and it will tell you. I think it was based on. It's obviously theorem proving, but I don't remember exactly how it was formulated. Okay. So next, I'd like to talk about convolutional neural networks. These are also called time delay neural networks because the first instance of architecture like this was called the time delay neural network. And the way it works is basically, as you read in the reading, for each kind of pair of vectors that are next to each other in time, you combine them together by doing an affine transform of the concatenation of the vectors and then doing a nonlinearity. And basically, the idea here is you take two neighboring word embeddings and you extract features from them. So a nonlinearity followed by a affine transform followed by a nonlinearity is our typical feature extractor. It's a feature extracting layer in a neural network. So we extract features from the first two words, we extract features from the second two words, we extract features from the third two words. So this is actually exactly the same as our bag of n-gram features, right? So our bag of n-gram features, we would extract features for each pair of words in the sentence. The difference here is that now we have kind of a soft feature extractor that can do all of the things that we liked when we were doing language modeling. It can do things like share information about similar words, etc. And then we combine all of these together in some operation. This is the pooling operation that was talked about. And then we can take the softmax and do probabilities. So this was called a time delay neural network when it was first invented in 1989 by Alex Waibel, who some of you might have seen around here. Convolutional nets are basically a 2D version of one-dimensional the one-dimensional time delay neural networks. So a convolutional net was used for image classification mainly. And because of this, instead of doing a one-dimensional step across a sentence or a speech waveform or some other one-dimensional thing, instead it does a two-dimensional step like this. Why do we call them convolutional neural networks in the framework of text is probably just because convolutional neural networks became popular more recently than time delay neural networks became popular. So if you want to call them time delay neural networks, it will make Alex Waibel very happy. So if you talk to him, you can be sure to do so. Because they're the same thing. So anyway, CNN. I'll call them CNNs because that's what most people call them nowadays. But CNNs for text. The first example of doing this in kind of the recent modern era that was also a very successful one is the Colabert and Weston paper. So they used a 1D convolution, which is basically a time delay neural network. But nowadays, people use a lot of terminology that originally came from images, so it's important to know this terminology to understand when people write about convolutional neural networks, even if you're talking about them in the framework of NLP. So, but anyway, so there's kind of two major paradigms where we use convolutional nets. So one is context window modeling, and this is for things like tagging, where you want to specifically model words within a particular window. And another one is sentence modeling, where you use it to extract information across the entire sentence. So the Collier and Weston convolutional architecture that they used for tagging, and they tried this on a whole bunch of different tagging tasks. If you haven't seen this paper is called Natural Language Processing parentheses almost from scratch, and it was a really big paper that kind of sparked the interest in neural networks for natural language processing nowadays. So they used this for a bunch of different tagging tasks, but basically they had a simple thing where they looked up the context windows, they ran them through a linear layer, a hard tanh, and then they had another linear layer to predict tags. So, so it's exactly the architecture that I talked about before. When you do it for sentence modeling, it's very similar, but you also have a pooling layer, specifically a max pooling layer, as was described in the text. So, as I said, convolutions were mainly developed in the image processing community. So, the functions that we use for convolution are very very often we use something called conv2D, which is the 2D convolution. And what it does is it basically takes input and parameters, where your input is a 3D tensor. The 3D tensor could be rows. Let's see. Actually, sorry, rows should be. Rows would usually be features of the word embedding. Columns would be words, and rows would be. Yeah, let me figure out my dimensions. I'll go back and look at I'll look at the code when I do the code example. But rows are words, or columns are words, and then features are channels. So the reason why this is called channels is because often when we have an image, we have our red channel and our green channel and our blue channel, and each of these have different pixel values for each position in the image. When we're doing something like text, we're doing something like just a vector. But we have lots of channels where each channel is one of the features of the word embedding. So like 256 or 512 channels, depending on the size of the word embedding. And then parameters, which are also called filters, are a 4-dimensional tensor where you have rows and columns, and then you also have input features, which is the size of the input, and then output features, which is the size of the output. So let's say you wanted to do a convolution that, I'll get to it in a second. Let's say you wanted to do a convolution that maps from 512 word embedding features to 256 output features. Then your input features size would be 512, and then your output would be 256. There was a question?
Yeah, so are you saying that a word embedding could also be like a 2D matrix?
So there are some architectures that use 2D matrices, but usually the word embedding, basically in convolution, we have a feature space, and then we have some sort of layout of things that have particular features. So in this case, the number of rows would be the number of words in the sentence. The number of columns would be 1, because we only, we don't have multiple sentences, we just have one sentence. And then the number of features would be 512, for example, if we have 512-dimensional word embeddings. Anything else? No? Okay. So there's concepts of padding and striding, which are important. So padding, basically what this, after convolution, the rows and columns of the tensor change size. So if they can either stay the same size, which is essentially means we pad the end or the beginning by a little bit to ensure that they stay the same size. So the reason why they would not stay the same size is because basically what convolution is doing is, as I showed before, taking in multiple vectors and turning them into ones. So if you don't do anything and you just apply convolution to each time step you have, the number of vectors reduces by the size of the width of the convolution minus 1. So because we have a width 2 convolution here, the number of vectors is reduced by 1 in our output. But padding and striding basically provide a way to adjust this. So you can either do a same convolution, which is basically you add one vector to the end of the sentence, like this. And so this is basically a padding vector filled with zeros. And then when you do your 2D convolution, you get something like this. And you still have the same number of vectors. Or you can do a narrow convolution, which reduces, or a wide convolution, which basically pads on either side, and this will actually increase the number of vectors. And there's also the idea of striding, which I think was covered in the book, which allows you to skip rows or columns. So if you do a stride of 2, you will skip a row every time. Yeah. Sure. Okay. So the wide convolution basically is you pad on this side also, which means that you'll get 1 extra instead of reducing by 1 in this case. So yeah, actually there is an advantage of this. So the advantage of using the wide convolution, for example, for text classification, is this could be padded by something like a beginning of sentence symbol. And if it's padded with a beginning of sentence symbol, you can extract features that say this word is appearing at the beginning of the sentence. So that's the advantage of wide. It gives you information about things that appeared on the boundaries. Any other questions? Yeah.
So usually like in computer vision, you pad it such that like the output would have the same dimension.
Mm-hmm.
Do you use also something like this for text, or do you want to keep like the different convolution also on the border?
So that's another option. That's the first one up there, the same convolution. And basically what that means is you would pad at the end. And this is useful because sometimes you don't want your lengths changing because it's just kind of annoying. So one other thing I should mention for striding. Striding is very useful if you have very long sequences because it reduces your sequence length by, if you have a stride of 2, it will reduce your sequence length by half. If you have a stride of 3, it will reduce your sequence length by 3. So it's very common to use striding in, for example, speech. Because in speech, you have a very long signal coming in, and you want to reduce its length by a bit. So this is a common thing to do there. So pooling was also covered in the reading, but just to go over very briefly. So each variety of pooling has a kind of intuitive interpretation about what you're trying to say about the features that you extracted. So pooling is taking a bunch of vectors and reducing them down into 1. And the most common way to do this is max pooling. And the reason why max pooling is very useful is because if you think of convolutions as feature extractors, it's telling you whether that feature existed somewhere in the sequence or not. So let's say you were trying to detect the n-gram do not like or something like that. If one of the features in your big feature tensor corresponds to the n-gram do not like, you'll detect it over all the n-grams in your input sentence, and then you'll take the max. So if it's detected anywhere in the sentence, the value will be 1. If it's not detected anywhere in the sentence, the value will be 0, for example. Another way is average pooling. So how prevalent is this feature over the entire range? This could be useful for things like where you want to extract a feature and you want to see how many of the frames include that feature. So an example of this would be like in speech, if you want to detect silence or how much silence there is. You might have a silence detecting feature. And then if you take the average, you could guess the ratio of silence in the speech waveform. There's also K-max pooling. So K-max pooling, this isn't actually used very much. It was used in the very early papers on convolution for NLP, and then I haven't really heard of anybody using it since then that much. But basically what this is doing is it takes the K-max instead of the max, and this allows you to say, how many times did you see this feature up to K times? If you've only seen it once, the first of the K-max will be 1 and the remaining 2 will not be 1. And if you've seen it 3 times, then all 3 of them will be large. Yeah.
So my understanding of the K-max was that you take the top K.
You take the top K values, but basically I guess that's correct, but what I want to say is, like, let's say we have 1, 0, 0, 0 versus 1, 0, 1, 1. Max pooling will not be able to tell the difference between these two examples, but K-max pooling will be able to. So K-max could tell you, oh yes, I have seen this 3 times. And then there's also something called dynamic pooling. So dynamic pooling is widely used in NLP, but I haven't really seen it used a whole bunch of other places. Although that might just be me not knowing about things. But basically, the idea of dynamic pooling is when we have variably linked sequences, we might want to know whether a feature appears at the beginning of the sentence, the middle of the sentence, or the end of the sentence. So what we do is we have something like 1, 0, 0, 1, 0.5, 0.8. And we reduce this dynamically linked sequence into a statically linked sequence, like maybe 3. So then we would count the number of times a feature appeared at the beginning, the number of times a feature appeared at the middle, and number of times it appeared at the end. So this would be like a dynamic like sum pooling, I guess. And then even if this sentence was 20 words long, you would just take the things at the beginning and put them in the first vector here, the middle, and the second vector here, etc. So I'll talk about some architectures that use this dynamic pooling a little bit later in the talk today. Okay, so I have an example of a CNN-based classifier. So I will do this. And the way, this is like all our other classifiers, so all the boilerplate code is the same. The only thing that's different is how we define our parameters and how we run this, how we run the classification task. So if we look here, when we define parameters for a CNN, remember the input of our CNN transform is 4-dimensional. It's the input has the number of words, the number of the input has the input is 3-dimensional, where the number of rows corresponds to the number of words. The number of columns is just 1 in the case of a sentence, and then the third dimension is the size of the embedding. So we're defining some parameters to look up something in the shape of 1 embedding size for each of the words in the sentence, and then we also have a window size. So this is the size of our convolution. In this case, we have a window of size 3. So this means we're going to be extracting basically trigram features from our sentence. Then we have, for the third and fourth dimensions of our CNN parameters, we have something equal to the embedding size and the filter size. So we take in the word embedding and we output features of size of filter size. And when we actually do classification, the way this works is we first look up all the words in our sentence. So this thing here will look up all of the words in our sentence, and then it will concatenate them together along a certain dimension. Yeah, sorry.
Why did we have to express the input in 3 dimensions if both of them are going to 1 or the 10? We can just have 1 and then the size.
So actually what we're doing here is we're concatenating. We're concatenating things together. So basically we're taking 10, 1, 1 embedding size tensors and we're concatenating them into one 10 embedding size, one big 110 embedding size tensor. So as a result, we get a single tensor representing all the words in the appropriate size for the convolution. So then we run the conv 2D operation. So the conv 2D operation takes in the input that we created. It uses the parameters of the convolution, and we calculate the stride. We set the stride to 1, so we don't do any striding, and we set our way of doing padding, and then we take the max along the dimension to do to basically extract the maximum. This is the max pooling part here, and then we do some reshaping of the tensor to get it in the right shape. We do a rectifier, which is our nonlinearity, and then we return the score based on these extracted features. So I know this is pretty fast. You can go back and take a look at it on your own after the class and ask questions if you're interested. One thing to note here is that despite the fact that we're processing an entire sentence, we're processing the entire sentence in a single convolution operation. The advantage of doing this is that convolutions are very, very fast on GPU, for example. So this is a very, very fast way of processing sentences and extracting features from them. And this is in contrast to stuff like recurrent neural networks, which I'll talk about next time. Yeah.
Is there a reason you don't do another nonlinear operation on the final score?
So this is calculating the score, and we calculate a softmax over it later, but this is the input to the softmax. Any other questions about that? So, yeah, the code examples, I'm not going to spend a huge amount of time on them in class because I think it takes more time than would be worth it in class to absorb everything. So you can go back and take a look later if you want. Yeah, sorry.
So the second dimension is 1 because you're processing one sentence at a time, or you're batching, because in dynamic dimension the batching system is automatic.
Right. So if you were doing batching, when you created your initial tensor full of things, you could do batches of. You could look up batches of words instead of single words themselves. This is unbatched. This example here is not using batching. So.
Each training example will be a sentence instead of a word, right? So
Yes.
that would be over sentences.
Exactly. Yes. Yep. So if you wanted to do that, what you would do basically is you would look up the first words in all of the sentences all at the same time. You would look up the second words in all of the sentences all at the same time, etc. As you step through the sentence.
And when you mentioned concatenation, what exactly are you concatenating?
So you're concatenating all of the. Yeah, actually, that's a good question. I'll go back and explain on the slides. So I think maybe this slide is a little bit deceptive about what's actually going on under the hood. So when you implement this, what you actually do is you look up all of the word embeddings here, and then you concatenate them all together into one tensor. So what you would be doing is you would basically be looking up I, hate, and this, and movie, and then concatenating them all into a single tensor. or that's what that concatenation operation is. Okay. So I will continue with this. So up until this was this was also covered in the Goldberg book, but there's a stacked convolution where basically you do multiple convolutions at the same time, multiple convolutions. Sorry, not at the same time, one after another. And the advantage of this is you can do things. You can get like an exponentially increasing view of the sentence. I don't know if this was explained super well in the book, but basically, one of the advantages of this is not that you go from 2 embeddings to bigram embeddings to trigram embeddings, but actually what you can do is you can go from bigrams to 4 grams to 8 grams to 16 grams in several steps. So you can get an exponentially increasing view of the sentence and actually capture a very wide context very easily. And depending on how big you set your convolutional filters and how big you set your stride will depend on, and how many layers you have will moderate how much your view of the sentence increases for each step. Yeah.
In the previous code example you mentioned,
yeah.
the entire thing was one convolution operation.
Yep.
What does that exactly mean, and how does it relate to what we are assuming convolution operations are happening?
So the one I talked about before was a single convolutional operation in the code example is of width 3, but basically it's only a single one of these. But you could imagine doing a convolution operation. You could imagine doing that same convolution operation one more time, and if you did it one more time, you would extract features over a while.
I guess where I'm getting confused is the striding part, like the whole striding over the sentence, one convolution operation, or is this just one multiplication inside a window, one convolution?
Oh, so the conv2D operation is over the entire sentence. It's a single operation over the entire sentence. And the fact that you can process the entire sentence in a single operation actually is very important for efficiency purposes. Yeah. Yeah.
So for the trying to, in order to exponentiate your detecting of span of sentence, in the region there is also called the dilated convolution, but that was achieved by changing the stride.
Right.
So, but I think in that way it seems to be that some information might be lost. And compared to what you said, you just simply larger windows.
Right. So the best way to get the kind of exponentiated, like increasing span of window is with the dilated convolution where you increase the stride. Or actually you don't even need to increase the stride. You just need to have a stride every time. So if you have a stride of 2 and a window of 2, your span that you're looking at will double every time. This is an example of a dilated convolution with a stride of 2. And at the first layer, you're looking at 2 characters. At the second layer, you're looking at 4 characters. At the third layer, you're looking at 8 characters. And at the fourth, you're looking at 16. So basically, every time you have a stride of 2, the number of vectors decreases by half, which allows you to kind of exponentiate the length of the thing you're looking at. Is that clear?
Yeah, but in this figure,
Yeah.
it seems that we are not actually doing stride. I mean,
So this is doing a stride here, and the reason why it's a stride is basically because if it wasn't doing a stride, we'd also have vectors in between each of these. So because it's skipping every other one, this is the definition of a stride. So this example here is a dilated is an example of one step of a dilated convolution. One thing that I'm sorry, is not very clear from this slide itself, or from the picture on this slide, is the difference between a regular convolution and what we normally call dilated convolution. And the dilated convolution, so this is like a regular, what I'm showing on here is a regular convolution with stride of 2. And we do four of them. But normally when we talk about dilated convolution, what we mean is we both have a stride and we do it at every time step. So basically, we will do a dilated convolution here that looks at the previous 16 characters. Then we'll also have a dilated convolution here that looks at the previous 16 characters, etc. So I guess we would have this example here, but it would be 1 for each time step. So the reason why something like this is useful is a normal convolution with a stride is very good for document classification, for example. Let's say you want to reduce a big document into a small number of vectors. To do that, you can reduce this I hate this film, all 16 characters of it, into a single vector using a regular strided convolution. But what you can't do is you couldn't do something like tagging, where you need a different vector for each character. So the dilated convolution allows you to both have 1 for each character, have 1 output vector for each character, and have this kind of wide stride. And it's also been used for things like predicting the next character in a character-based language model, for example. And you can do this. Because the dilated convolution calculates something at each time step. Are there any questions here? No. Yeah.
Can you explain the difference again between stacked convolution? Like if suppose the stride is 2 figures also, both of them are.
Okay, so a stacked convolution is basically just multiple layers of convolution stacked one after another. So I guess dilated convolution is one example of a stacked convolution. Let me draw an example of dilated convolution on the board. So basically we have, it will be a simpler one, but we have I hate it. And you will have you will extract bigrams for every, you'll extract things with bigrams for every one. And then in the next one, you extract features for pairs of vectors, but they skip over one vector. But unlike a regular strided convolution wouldn't calculate this one here. But when we talk about dilated convolution, we're talking about one that still calculates them for every piece of the sequence, I guess. Yeah, sorry. I should really change this slide. I realized this was confusing after I looked at it. As a quick aside, up until now, I've been talking about nonlinearities, which are essential in neural networks to kind of extract features. The proper choice in very simple networks, like networks that have one layer, the choice of the nonlinearity actually doesn't have such a huge effect. But as we start adding more layers, like if we have more layers of convolutions, etc., it ends up having a relatively large effect on our accuracy. And there's a bunch of different nonlinear functions that you could think of. Maybe the simplest nonlinear function is the step function, where anything less than 0 is set to 0. Anything greater than 0 is set to 1. So does anyone know why this is a bad function for training neural networks? No, this is actually differentiable. You can calculate the gradient of it just about anywhere, or it's subdifferentiable at least. What's that?
Zero gradient everywhere.
Yeah, it has 0 gradient everywhere. And something that has a 0 gradient just about everywhere is something that's called piecewise constant. And so this is a piecewise constant function that has a 0 gradient everywhere. And if you get a 0 gradient, you can't do backpropagation. Well, when you do backpropagation through it, your gradient becomes 0, and you lose all your training signal to previous things, to previous parts of the network. So instead of this, we use the tanh function, which is smooth and has a non-zero gradient everywhere. The problem with the tanh function is, so what's the problem with the tanh function? It saturates very quick, yes. So to put it in other words, its gradient is very close to 0 almost everywhere. So in the very middle, the tanh has a gradient that's not 0, but almost everywhere else in the extreme high parts and the extreme low parts, the gradient becomes 0. And anywhere where the gradient is 0, your net becomes very difficult to train. So because of this, people have done this. People have come up with other things. A very popular one is the rectified linear unit. And the rectified linear unit is basically a thing where it's linear if the value is greater than 0, and it's 0. The value is 0 if the gradient is, or if the gradient is, sorry, the output value is 0 if the input value is less than 0. And here the gradient is 0 for any value less than 0, but the gradient is non-zero for any other value. So this tends to not saturate as well as easily. This has its own problems because the gradient is 0 in a lot of places. There's also things like soft plus. There's, probably the most interesting recent paper on this is something called self-normalizing neural networks, which proposes something called CELU. What's the SAT stand for?
Self-normalized exponential linear unit.
So the self-normalized exponential linear unit. So if you want the hottest activation function, you can take a look at it. But actually, it's probably not the hottest anymore. There's probably a new hotter one because that paper came out like 3 months ago, which is ages in neural network land. Okay. So why would we want to use convolutions for modeling sentences? So there are some very good reasons for using convolutions. So this is in contrast to largely in contrast to recurrent neural networks next class. So I'll go back and revisit it at that point. But convolutions, if you're familiar with recurrent neural networks, basically, if you're not familiar, basically what they do is they step one word at a time through the entire sentence, which means they make n steps through the sentence in order to process the whole thing. So compared to that, convolutions, for example, a dilated convolution, to calculate the representation for a sentence would need about log n steps, because you can reduce the size of the sentence by half each time. Another thing that CNNs are very good at is they're very easy to parallelize on GPUs, because unlike a recurrent neural network, which needs n operations to process a sentence of length n, convolutions can be processed in a single GPU call, which makes them very fast. One thing that's difficult about these is they're less natural to use for example, arbitrary length dependencies. I'll talk about why RNNs are good at this. Also on CPU, they're a bit slower. They tend to be a bit slower, but it's kind of in the margin of error, I guess. Okay. So this was, yeah, sorry.
Slightly orthogonal question. Are there ways to learn weights for these networks besides gradient descent or backpropagation, which doesn't require these loss functions to be differentiable at all?
That's a good question. I'd say yes, but they're not as good usually. So one way you could do it is you could randomly pick a whole bunch of weights and just do that over and over again until you find a good network. It sounds pretty ridiculous, but if you have a really small and trivial network, or really small and trivial function that you want to calculate, it does work sometimes. There's other things like genetic algorithms, or they're called like evolution strategies sometimes, which is where you kind of do random search in space. But in general, gradients are really, really strong signals. So anything that you try to do without a gradient will be a lot harder than if you try to do it with a gradient, which is why almost everybody uses gradient descent, I think. There are ways to handle non-differentiable functions in neural networks, which I'll be talking about in later classes. Any other questions? Yeah.
Like in the equivalent, like from images, do we have different kernels over here for convolution?
Oh yes, actually, that's very important. But I think I'm going to talk about it later. But it's very common to have different kernels for, or different widths, different filter widths. So you have a filter width of 1, and then 2, and then 3, and you use all of them together. So, okay. So next, I'm going to talk a little bit about structured convolution. So this is some. Yeah, sorry.
I'm sorry, just going off that point.
Yeah.
For the separate filters, would you just reshape them all?
So what you normally do is, let's say you have filters of length 1 and length 2 and length 3. What you do is you do your length 1 convolution, then you do the max. You do the max pooling or whatever pooling you do. Then you do the 2, you do max pooling, 3 max pooling, and then you concatenate everything together before you make your final decision. Okay, so structured convolution, the idea here is that language has structure, and we would like to use it to improve our feature extraction. So one example is noun-verb pairs are very informative, but they're very difficult to capture with normal CNNs. So normal CNNs just look at local context windows, and you can tell something like a noun is a object of a verb or something like that. So one example of how people can do this is by using dependency structures. So if we have a dependency structure, basically this tells us, okay, engines is the object of makes. And a way that people have proposed to do this is through, or there's a couple ways people have proposed to do this. One way is tree structured convolution. So the idea is you manually define kernels that are defined over subtrees of the tree. So if you want to say, if you have a particular node that you're interested in extracting features from, you extract its parent, and its grandparent, you extract its sibling or something like this, and you create convolutional kernels defined over this. So this is like an extension of the unigram, bigram, trigram, except it's defined over tree structures. And this is kind of an interesting way of doing things, but there's two difficulties. One is that you have to manually define these feature templates yourself. The second problem is that none of these are very easy. This is not super easy to implement if you want to implement it efficiently. Yeah.
So how do these compare against recursive networks or something?
How do these compare against recursive networks? That's a good question. I haven't looked at the results table of this paper for a while, so I don't remember if they compared. But Recursive networks are networks that are defined over tree structures, and they basically are kind of like the equivalent of a recurrent neural network, but generalized to trees. These convolutions are like convolutions generalized to trees. And my general kind of impression of convolutions versus recurrent neural networks is that convolutions are generally very good for classification tasks, and recurrent neural networks are good for like other tasks. And recurrent neural networks are good if you want to synthesize a lot more information than just like what is the class of this sentence. So my guess is that for things like classification, this would work better than recursive networks, but I'd have to go back and look at the results to see. Another thing that has had some promising results recently is graph convolution. So the idea of a graph convolution is this is not even limited to trees. It can be used over arbitrary graphs. And if you treat a graph as if you treat a sentence as words that are nodes and then edges between the words, you can see this as a graph. And the way a graph convolution works is basically when you calculate the feature vector for the word the next time, you multiply the word itself by a matrix. You also multiply all of its neighbors by a matrix, and these matrices, parameter matrices, are defined by the relationship between the nodes. So, for example, if we look at lane disputed, the representation for lane after a graph convolution would be the embedding of lane, or I'll call the embedding x, times W self, and the embedding of disputed times W subject. And this would be like the hidden state for lane. And then similarly, the hidden state for, or the features for disputed would be disputed times the self matrix, lane times the like subject matrix, or subject minus one matrix, and then estimates times the object matrix. And the reason why this is interesting is because, as I said before, one of the things we would like to know is relationships between, say, makes and engines. Like, we want to know that we're not, another thing that we could be making is a ruckus, right? So if we say makes engines versus makes a ruckus, for example, the translation of makes would probably change in another language. So what this allows us to do is this allows us to pass information along these dependency edges to modify all of the words in the sentence. Are there any questions about this? Yeah.
In the original convolutions, the intermediate features represented engrams also.
Yep.
But here you said the hidden representation is of the word lane itself. But
Yeah.
what do the intermediate features represent in graph convolutions?
So that's a good question. So let's say we used the same convolution in the or what shall we do? Yeah. So let's say we use the basically the same convolution during a regular convolution. In this case, you can basically say that there's kind of a one-to-one correspondence between the inputs and the outputs of this, because you're padding it to the appropriate size to make sure that happens, etc. And actually, convolutions themselves are a subset of graph convolutions. So if you think about this, this is basically a graph convolution where we have a single matrix for the word itself, and then we have a matrix for its right neighbor. So you can kind of view regular convolutions as graph convolutions as well. This is just a more general framework that allows you to do things across long distances, etc. Yeah.
So what if we have different number of edges? So does the filter change?
Yes, it does. So the filter doesn't change. One of the nice things about the graph convolution is this can take an arbitrary number of edges. So you see Lane disputed. So Lane and disputed, there's only one neighbor of Lane, so there would be two elements to this addition here, Lane itself and its neighbor. And then for disputed, it has two neighbors, so there would be three elements to this addition. And it's as simple as that. You can note that this will limit your expressiveness in some way because, for example, if you have two right neighbors and they both have the same dependency arc, you won't be able to distinguish between them when you're calculating your, yeah.
Isn't this the exact same thing as the recursive network? Like, don't they do the exact same things?
This is pretty similar to a recursive network, maybe defined over. Yeah, it's pretty similar. So it's normally the recursive network was defined kind of in a binary way.
But then for like dependency process and all, you have weights for different dependency relationships.
Yeah, that might be a good point. I had actually forgotten that the recursive network. I'd forgotten that the recursive network had done things with weights for dependency arcs and something. So I should go back and look at that and make sure, like, what the relationship is between them. But I think there's a very high probability that you're right, that they are actually very similar or even the same. Okay. So I will, next I will talk about convolutional models of sentence pairs. So this is useful if you want to model not one sentence, but pairs of sentences. And there's lots of reasons why you would want to do this. For example, paraphrase identification. You want to know if these multiple sentences are the same meaning, or sentence similarity, where you want to know whether they're similar in some way. Also, textual entailment. So textual entailment is whether one sentence is entailed by the other, or you can deduce the information. Also, retrieval, etc. So kind of the first architecture to model pairs of sentences, pairs of sequences, I guess, is a better way to put it, is called a Siamese network. So the way a Siamese network works is it's just two feature extraction networks, where each feature extraction network has the same shape as the other. Or it has it's the same operation as the other. So if you put a sentence in, the feature extraction for the two sentences will be exactly the same. And then in the end, you get two vectors. Of course, if they're exactly the same sentence, you'll get exactly the same vector. But if the sentences are slightly different, then if they're only slightly different, the vectors will probably be very similar. If the sentences are completely different, then you'll get very different vectors. So this is maybe the most trivial way of modeling pairs of sentences. The good thing about this is it's simple, and also you get a single vector, a single sentence representation in vector space. Yeah, sorry.
The weights are tied for both networks?
Yes, usually they are. Of course, you can do this without tying the weights for both networks. And you would probably want to do that if you were modeling, for example, one language in another language, like English and Chinese or something. You might not want to, though. You might want to share the weights for English and Chinese. So.
What's the loss function? Are you trying to say that both sentences are the same?
So the loss function can be an arbitrary loss function, anything you want. So basically, what this does is this gives you two vectors, and then you can use them whichever way you want. Some ways you could do it. Some popular ways are if you want to do something like sentence retrieval, you will randomly sample negative examples, and you'll try to make the score or the similarity of the true corresponding examples higher than the other ones. There's also, you could also just try to regress to the sentence similarity evaluation. So like, let's say you had a human evaluation of sentence similarity from 1 to 5. You could just put the 2 vectors in and try to predict that, that sentence similarity score. So, whatever you want to do, but it's very common to use the kind of like negative sampling one. And we're going to talk about that more in 2 classes, I guess, next Thursday. Okay. So the reason why I'm talking about this here in this class on convolution is that actually kind of the state of the art in sentence pair modeling almost always uses these, or very often uses these convolutional networks. And up until now, I've been talking about one-dimensional convolutions because sentences are one-dimensional. So now we finally have our reason to use 2-dimensional convolutions in an NLP problem. So now we can use all the architecture that image processing people created for us. So this is one example. It's called the convolutional matching model, very, very aptly named. So.
Was the wording you used on purpose? I mean, is it like I want to use 2D convolution models? So what, I mean, is that how it happens?
No, it's a joke. Sorry, but sometimes I'm a little bit sarcastic, and that doesn't come across very well. Just to make things perfectly clear, when I do research, I do not do things because I want to use a tool. I use a tool because I want to solve problems. So if I say something otherwise, I'm joking. So, yeah, but good question. So the way we can do this is basically. So the 1D convolution, the thing they say 1D convolution here is a little bit deceptive. But basically, what they do is they take sentence S. They take sentence S Y and sentence SX. So sentence SX is our source sentence. Sentence SY is our, or I guess they're both sentences that we want to match in some way. And what you do is you basically stack these into a 2D matrix, and then you step over all pairs of 3 word segments, and you apply a convolution that isn't a 3x1 filter. Like this. So our original filter was over basically all of the features in this 1, 2, 3, like x1, x2, x3, or x2, x3, x4. But we instead step over x1, x2, x3, and y1, y2, y3. And then these are pairs of 3 words in the source. These are pairs of 3 words in the target, and then we have features for all of these words, which are kind of our embeddings, for the words. And by doing this, basically what this allows us to do,
What is each entry of the matrix?
So each entry of the matrix is, let me try to be careful so I don't make a mistake. I believe each entry of the matrix here is the source of that position concatenated with the target of that position.
Can you give an example of that?
Yeah. So so the first, basically what you do is you concatenate in feature space, you concatenate xi with yj, and this becomes, I'll call it f, feature ij in this feature matrix.
So it's not a matrix. It's not
Sorry, tensor, feature tensor, yeah, a 3D feature tensor.
But then, so it's a 4D then, because there were other features as well, for words or pause tags or something like that.
Those are the features X.
Yeah, they're
of the vector
included
X.
in vector xi, yj, yeah.
So just to clarify, you
Yeah.
have the concatenation of the two, you have a matrix
Mhm.
of those concatenations, and then that third dimension is the kernels extracted over.
Yes.
Yeah, but actually, how to do this is probably task dependent. I mean, if you're not doing matching exactly, then your combination, you can add them or you can match them.
Yeah, there's a paper on recognizing textual entailment where they multiply each coordinate between the center instead of concatenating.
Mhm.
Yeah, it depends.
What, do you know the name of the paper?
No, it's very recent. I don't know.
Okay. So, yeah, what's that? Okay.
Just go to the SNLI page and if you look at the leaderboard, it's there.
Okay, so if you go to the Stanford Natural Language Inference page and go to the leaderboard, apparently it's near the top of
It's
the
also
leaderboard.
there in the book, like
Okay.
the Yao book,
Okay.
case study chapter. That's there.
Oh, okay. I did not see that. So. Okay. But anyway, so this is a much better way of modeling sentence pairs than something like it's a much more effective way empirically. And the reason why is basically because what you're expecting the network to do if you model them using a Siamese network is to extract all of the information that's relevant for all of the comparisons that you want to make into a single vector. And that is a lot to expect your network to do without knowing a priori what you want it to compare to. So if I told you, please read this sentence, now please read this other sentence, and how similar are they? You'd probably have trouble, comparing the details of the sentences, because it would test your memory. And this is not testing the memory because you can compare them directly. Yeah.
Would you use this kind of architecture for machine translation tasks, or only for
This particular architecture would not work very well for the machine translation task directly, and the reason why is because you basically need to know the sentences in advance to calculate this. That being said, there are convolutional architectures for neural machine translation, but I will talk about them in the neural machine translation or in the sequence-to-sequence model place. So I don't. There's a few issues there that I'd like to cover first before I talk about them. So I'll talk about them there. So then, if you want to get really crazy, what you can do is you can stack up a whole bunch of convolution operations, a whole bunch of pooling operations. So this one, what it does basically is it has it has a stacked convolution where each stack gradually increases the granularity of the features. So it's the low-level features are very short n-grams, for example, and the high-level features are very long ones. And it extracts, it pulls together these features at each level, and then combines all of these together to make a similarity judgment. And this works well, but adds more complexity over the model that I just described. And because the class time is done, I will not talk about visualization this time, and I'll try to talk about it. I'll try to talk about it next time. But just to give a hint, I'm going to talk about lots of beautiful pictures that can help us develop it.